Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to look at another electronic quiz. Here it's our circuit with MOSFET transistors, and we're looking at Rout. We're going to calculate Rout in this circuit, and here these are our assumptions for transconductances of these MOSFET transistors. And be careful, lambda is equal to 0, which means that we're going to neglect the channel length modulation. But if you're new here, please give me a thumbs up, hit that subscribe button, and also the notification bell, so whenever I upload a new video you'll be aware of it. Let's jump into it. Here it's our circuit, and these are our assumptions, and here are the possible answers for this question. So what is the method that we're going to use to calculate Rout? Well, here is the situation. For calculation of Rout, you had to put a voltage test at the output, and you can call it anything you like. For example, Vx for this node, and this is the current through this node Ix, and by the definition this Rout is going to be the proportion of Vx divided by Ix, whenever Vin, which is the input voltage, is 0. So in order to calculate Rout for this amplifier, we had to connect this Vin to the ground. So there is no gate for this M1 transistor in here. Now I'm going to use a small signal model, which is pretty simple in here because we only have GM, the gate source of the transistor, and then GM VGS. This is the main point. Okay, this is a small signal model that we use. You see, this is gate, this is source, so VGS, and the direction of current is going to be GM VGS from drain to the source. And if you use another polarity voltage for VGS, for example, if you put plus sign of VGS on the source, this direction of the current had to be vice versa, in reverse actually. So be careful about the direction. And another thing, this is a VDD voltage, so again this had to be in grounded when you calculate Rout. Okay, all the DC sources had to be eliminated, in addition to Vin, which is going to be short connected to the ground. Now I'm going to use this a small signal model for this amplifier to draw some equations from it. Okay, but in order to calculate these, I had to define a new voltage. Let me call this voltage with another color. This is a voltage node that we had to define it. For example, I define it Vy new variable, in addition to Vx and Ix. But you don't need another variable in here. So this is Vy for gate transistor of M4, and because the source is grounded, so GM4 times Vy is the drain current through this direction. GM4 is 6, so 6 Vy for this transistor in here. How about M2? M2, this is Vy, and M2 GM2. GM2 is 8, so 8 times Vy for this transistor. And how about M3? M3 is PMOS transistor, but nothing is changing here. You see, when we talked about a small signal model, I told you this is important. If you take the plus sign on the gate, the direction of the GM VGS is going to be from drain to the source. I didn't say that if this is NMOS or PMOS transistor. It's just the same principle for both transistors. So be careful about this. Most of the times students confuse this two together. So Vy gate and source is grounded, so again GM3 times Vy is in this direction. GM3 is 2. So 2 Vy for this transistor. And how about M1? M1, the gate, again this is PMOS, but no important. The gate is grounded. So how about source? Source is connected to the Vx. So because source is connected to the Vx, the plus sign of VGS is in source. So the direction of the current for M1 is going to be from source to the drain, not in reverse. Okay? So for M1, GM1, which is 2 times V source gate in here actually, which is Vx. Because the gate is grounded, so Vx minus 0 is Vx. An interesting thing happening here. Look at these two. These two are equal. This drain current of M1 is going to M2. So we can simply write this equation. 2Vx equals to 8 Vy. Now we can set that Vy equals to 1 divided by 4 Vx. Okay? This is the first equation that we need. Now we're going to use KCL. KCL at this node, at the output, when we want to calculate our out. KCL at V out at this node. So all the current through this node. Ix is going to be inside this node, so minus Ix. 2 Vy in the outside plus 2 Vy plus this current, this is 6 Vy, and this current, no important, you can write 2 Vx or 8 Vy, both of them are the same, plus 2 Vx. So we're looking for the proportion of Vx divided by Ix. So if this equation is just in terms of Vx and Ix, we're done. The only thing that's different is Vy. So I'm going to substitute this Vy in terms of Vx into this equation to get rid of Vy in this KCL. And the problem solved. So minus Ix plus 2 plus 6 is 8 Vy. And instead of Vy, I'm going to use this substitution, Vx divided by 4 plus 2 Vx equals to 0. So 8 divided by 4 is 2 Vx plus 2 Vx, 4 Vx, and I'm going to change minus Ix and move it to the right hand side of the equation. So here Vx divided by Ix, which is our R out, is 1 divided by 4. But what is the unit for this R out? Because GM is in milliampere volt, so this R out had to be in kilo ohm. So 1 divided by 4 kilo ohm equals to 1000 divided by 4 ohm, which is equal to 250 ohm. So the right answer is option A. As you can see, I'm just using a small signal model and KCL at the output node, and tada, problem solved. Okay, if you guys have any questions relating to this problem, please let me know in the comment section. And if you like this video, please give me a thumbs up, share this video with your friend. I will see you on the next video. Thanks for watching.